In this lesson, we're going to talk about Chapter 5, Section 2, Independent and Dependent Probability. I want to start first with a little bit of vocabulary for you to put in your notes. We start with independent events, and independent events are two events when the occurrence of one event does not affect the occurrence of another event. So now instead of just talking about one thing happening, we'll be talking about one thing happening and then something else. For example, you flip a coin and then you roll a die. Does what happens the first time affect what happens the second time? The events are going to be dependent events when the first occurrence does affect the occurrence of the second event. And then the last thing is conditional probability, and that's used with dependent events. It's talking about that second probability that has been changed because of the first one. So you'll want to go ahead and pause and jot down those definitions before you move on. I want to start talking about the independent events, and those were the ones where we said the first one doesn't affect the second one. So if you roll a die and then you flip a coin, does what you get on the die affect what you can get on the coin? And the answer is no, they don't affect each other at all. So those would be independent events. If I flip a coin 4 times, does what I get on the first affect the second, or the third, or the fourth? No, each flip is independent of itself. So that's another example of independent events. And then what about choosing 2 books out of 6 on a shelf? So if there's 6 books and you pull one of them, does that affect what you can pull for the second book? For that, the answer is yes. So this one would not be an example of independent. That would be dependent. I wanted to give you a little bit of both. When we're talking about the probability of independent events, the way we find the probability of A happening and then B happening is to multiply the probability of A times the probability of B. So let's say we roll 2 dice, and we want to know what's the probability of rolling a 3 and then an odd. Well, if we look at our chart, we know there's 36 total outcomes, and 1, 2, 3 of them involve rolling a 3 and then an odd. So that would be 3 out of 36, which is 1/12. But if we didn't have it, then we could still figure that out. We're going to do the probability of rolling a 3, which is 1/6, times the probability of rolling an odd, which is 1/2. And 1/6 times 1/2 is 1/12, which is the same. What about the probability of rolling 2 evens? Well, if we look here, 2 evens would be a 2 and a 2, a 2 and a 4, a 2 and a 6, 4 and 2, 4 and 4, 4 and 6, 6 and 2, 6 and 4, or 6 and 6. So that was 9 outcomes out of the 36. 9/36 is 1/4. But the way to use the formula is to say 2 evens. Well, the probability that the first one is even is 1/2, times the probability that the second one is even, which is also 1/2, and 1/2 times 1/2 is 1/4. So go ahead and jot those examples down. Oh, that was the dog. Okay, let's do a little bit of practice determining whether events are independent or not. So in our first example, you have 3 white golf balls and 2 yellow golf balls in a bag. You randomly select one to hit now, and then you place another one in your pocket. So you pick one to hit, and then you pick one to put in your pocket. And this says use a sample space to determine whether randomly selecting a white golf ball first and then a white golf ball second are independent events. So we want to think about what we have. Let's see. We have white, 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 yellow, yellow. Well, the probability that the first one we select is white is 3 out of 5. But is the probability of selecting a white golf ball, does it change when we put the first one down to hit? Well, when we hit this golf ball, it changes the total number in our sample space, and so this is a dependent event. Our second problem says your friend writes down a phone number on a piece of paper, but the last 3 numbers get smudged after being in your pocket all day long. You decide to randomly choose 3 numbers for each of the 3 digits. Use a sample space to determine whether guessing the first digit correctly and the second digit correctly are independent events. So when you think about the sample space for this, for each of the 3 numbers that you're going to choose, you have 3 numbers, 1, 2, 3, and you have the numbers 0 through 9 to choose from. Well, does what we select here for 0 through 9 affect what we can put here? So think about things like, if we select a 1, can we select a 1 again? And the answer is yes. So the probability that we choose the correct one on this one is 1/10, but selecting the correct one on this one is also 1/10. So this is independent. What we choose here doesn't affect what we choose here. On this one, we're trying to guess a 3-letter password that uses the letters A, E, I, O, U, and Y. The letters can be used more than once, and they want us to find the probability that we choose the correct password, which is U. Well, let's see. We're going to choose 3 letters. Whoa, those are pretty bad. Let's try again. 1, 2, 3. And we have the letters A, E, I, O, U, and Y to choose from, which means we have 6 letters to choose from. What is the probability that the first one we choose is a Y? Well, if we're randomly choosing, the probability that we choose a Y is 1 out of 6. Now, we've chosen a Y, but since we can use the letters more than once, the Y stays in our group of choices. What's the probability now that we choose an O for the second one? Well, there's only one O, so it's 1 out of 6. And then what's the probability that we choose a U for the last one? Well, there's one U in our sample space, so it's 1 out of the 6 letters. And we're going to multiply those together. 1 times 1 times 1 is 1. And 6 times 6 times 6 is 216. So we have a probability of 1 out of 216 to guess it correctly. Now we're going to switch and talk about dependent events. So dependent is where the first thing that's happening affects the occurrence of the next event to happen. So this might be something like choosing 2 names out of a hat. Once I've chosen the first name, I'm not going to put it back in. I'm going to choose another name. And so what I choose first affects what I choose second. What about randomly choosing 2 cards from a deck? Well, once I've taken the first card, it's no longer still in the deck, so it's gone from 52 cards to 51 cards. So the probability of what I choose for the second has changed. So that's dependent events. When we're talking about the probability of dependent events, the setup is essentially the same. We're going to do the probability of A times the probability of B. But this time, when we find the probability of B, we have to assume that A has already occurred. So we say this is the probability of B after A has occurred. So if we're talking about this in example 2, the probability that we choose a girl first and a girl second, we didn't talk about this example. But the probability of choosing a girl first was apparently 9 out of 12. But once we've chosen that girl, there aren't as many girls to choose from. So that would change the probability of the second event. I'm not sure where these numbers are coming from. We'll have to look at that. But let's do some examples where we know that where the numbers are coming from. Here, let's say we want the probability of drawing a yellow marble and then a red marble. Well, if we want, we could write out all of the possibilities right here. And so a yellow and then a red, there's only one outcome like that, and it's right here, 1 out of the 20. But we don't always want to write out the sample space. So let's think about what's the probability of drawing a yellow marble. Well, there's 1 yellow marble out of 5. So the probability that I draw that is 1/5. Then I want to multiply that times the probability of drawing a red. Well, initially, the probability of drawing a red was also 1 out of 5. But once I've taken this out, now the probability of drawing a red is 1 out of 4. So 1/4 is going to be the probability of drawing a red. 1 times 1, 5 times 4 And the probability of drawing a yellow and then a red is 1/20th, just like we said when we were looking at this sample space here. Let's go back to that trying to guess the 3-letter password. What if we can't use the numbers more than once? We still have the same 6 letters, A, E, I, O, U, and Y, but we can only use each letter one time. So if we have 3 to choose from, or 3 letters to choose to get the password, the probability that we choose an A, well, there's one A out of 6, so that's 1/6. But assuming that we've drawn the A, it's no longer in our choice of letters. So what's the probability we choose an I? Well, now there's 5 letters, so the probability of drawing an I is 1 out of 5. Now I've drawn the I. What's the probability that the last one I draw is an E? Well, there's one E out of the 4 letters left, so 1 out of 4. Pardon the drawing, I'm using a mouse instead of a stylus. And so when we multiply those together, we get 1 out of 30 times 4 is 120. So we have a 1 in 120th chance of getting it correct. You see that our chances got better for guessing the correct password. Before, it was 1 out of 216 when we could repeat the letters. But when we can't repeat the letters, now we have 1 out of 120. Now, sometimes you're given a table. So this one shows the number of male and female college students who played collegiate basketball and collegiate soccer in the United States. Part A says to find the probability that a randomly selected soccer player is female. So we assume, first of all, that the first thing has happened. We've chosen a soccer player. What's the probability that that soccer player is female? So we're going to do 36,523 out over the total when we add those two together. Then when they want us to find the probability that a randomly selected male student is a collegiate basketball player, then when we look at this, we have to assume, first of all, that we're selecting a male, so we would only look at this one. And then we want the probability that it's a basketball player, so we would do the number of basketball players over the total number of male athletes. And that's our lesson.